Hello everyone, this video is for Baeyer Villiger oxidation where I will focus on mechanism, regioselectivity and chemoselectivity. So let's start. So here you can see the reaction. I have taken a substrate which is ketone. On one side there is a group Rm. Now why what this M it signifies? It signifies the migrating group. Once you will see the mechanism, it will be clear what is migrating group. And another side we have R group. So both side there will be some group. It is a ketone compound. The reagent is par acid. So as you can see here we have oxygen-oxygen bond. So this acid is par acid, and in the product side we are seeing A star. Now if this Rm and R, these two are connected, then you will get lactone, that is cyclic ester. Cyclic ester is lactone. So if these two groups are connected, you will get lactone, and that depends whether your ketone is cyclic or acyclic. And the fate of this par acid is now it is converted to carboxylic acid, because one of these oxygen, from the color you can understand, now it is inserted between the Rm and the CO. Now oxygen will be inserted only between the migrating group and the C double bond O, not between the C double bond O and other group. Now this par acid, depending on what type of R prime you have taken, there may be different variety. So in this table you can see, depending on what is your R prime, it may be H, CH3, CF3, PH, and then we have this metachloroparbenzoic acid. So instead of pH group, if at meta position you have chlorine, this reagent is called metachloroparbenzoic acid. So this is the connection point that I have drawn in this way. Now sometimes hydrogen peroxide or its masked form, which is this compound, right? bis-trimethyl peroxide, this type of compounds are also used. But important point is this oxygen-oxygen, that is this linkage, that is present. Next we will go to the mechanism, right? So here the first attack will be addition to carbonyl compound. So this oxygen, that is OH, this lone pair, if it is attacking at this carbonyl carbon, there will be negative charge over this oxygen, right? So this is very simple. So here in the right hand side you can see negative charge over this oxygen, and this oxygen is now positively charged. Next there will be a proton exchange. So this hydrogen, now it will come to this O minus, and the right hand side positively charged oxygen will be now neutral. So it will be something like this, and this is a tetrahedral intermediate. Now in this tetrahedral intermediate there will be something interesting happening, and this is basically the migration. Now the Rm group will be migrating, not this R. Now on what are the factors on which this migration depends, whether it is this left hand side group or right hand side group, that I will discuss separately. Right now just consider this Rm as the migrating group. So what happened here, what will happen here, this lone pair, if it is making a double bond, now this Rm, it will be migrating to this oxygen, right? And this oxygen-oxygen bond is already weak, because you know this lone pair, because of this lone pair repulsion, this oxygen-oxygen bonds is very weak. So there will be negative charge over this oxygen. So now there will be a connection between Rm and oxygen. This bond is broken and there will be a double bond at this position. So everything is happening concerted with. Okay, this is the uniqueness of this mechanism. And after this we are getting, look at the left hand side. So this is from the, when there is negative charge over this oxygen, you are getting from the right hand side part RCOO minus, R prime CO minus, and here we have this, we have reached our product, only the difference is here you have some extra hydrogen. So after deprotonation, this hydrogen can be going towards this RCO2 minus, and finally we are getting our product. So you can see this oxygen is inserted between C double bond O and the migrating group. And as I have said, if this you have started with some cyclic ketone like this, then you will get there will be a expansion in the ring size. So initially if it is 5 member, now it will be 6 member because of this extra oxygen atom. Now some important points regarding this mechanism. What is the support behind this general mechanism? General mechanism, I mean, first there is addition to carbonyl, then there is proton exchange, migration. So this is a general mechanism. So the reaction is catalyzed by acid. Suppose in presence of acid, this oxygen, that is our substrate, that will be protonated. So this type of attack by this OH, that is a lone, it is a basically nucleophilic attack, or you can say addition to carbonyl, that will be very facilitated, right? So catalyzed by acid and is accelerated by electron donating group in the ketone. That means if this Rm group, there is some electron donating part, because when it is moving towards this oxygen, there will be some positive charge generation. So this Rm, it should be such so that it can stabilize this positive charge. Everything will be clear in the next slide when we will actually see the transition state. So electron donating group present, it will facilitate this type of migration, basically in this Rm group, and electron withdrawing group in the par acid, because after all this part is removed as RCO2 minus. So suppose there is some electron withdrawing group present, it will be able to stabilize this negative charge. So that these are the support. And what is the support behind this intramolecular concerted nature that you can see in this tetrahedral intermediate? There is a complete retention of configuration at the migrating carbon. So if you have some chiral center, this stereochemical integrity is maintained. So these are the supports for the mechanism. That is the general mechanism as well as the concerted nature of this migration that is occurring in this tetrahedral intermediate. Now we will focus on regioselectivity, and that depends on the ease of migration. So as I have said, suppose your ketone is unsymmetrical, it may be cyclic also, but both sides there will be different types of groups. And now you are doing this reaction, so there are two possibilities. You will get this or you will get the other one. That means oxygen is inserted either between R and CO or between R prime and CO. Now which one will happen, that is basically, that depends on which group will migrate. So these two are, that is, if one of these you are getting more, that means your reaction is regioselective. So one of them will be, we will be getting suppose 100% or maybe in higher amount, that is a major product. Now the design behind this specific group migration, because we always get regioselective reactions, so only one group will be specifically migrating. But what is the, how we can decide that? So for that we have to understand this. See, this picture I have taken from Clayden. I have also given the page number. You can also, if you are interested in details, you can check there. So see, suppose one of these group is methyl group, that is in the left hand side, and the other side we have some isopropyl group or maybe any secondary, that is, this is the connection point, this carbon is secondary carbon, there may be any other connection or it is simply isopropyl. So what I am trying to say, on one side there is methyl group and another side there is more electron donating group present, right? Now see what is happening here. When this lone pair, it is making a double bond in the transition state. This is the transition state. So there is some positive charge generation at these positions, because this bond is going to break. This double bond is will be formed, and this bond is also dotted. That means there will be this bond is going to break, right? And also this oxygen carbon bond that is going to form, right? So this bond is breaking, there will be a new bond formed at these positions. So now you can see the positive charge generation and the negative charge generation. Now here if you read, you will see that the transition state, positive charge spread out over the molecule as the carboxylate leaves as an anion. So this part is removed as anion, because ultimately this is your product and the other part will be something like this. So if the migrating group can take some responsibility for this positive charge, so this type of positive charge generation that you can see here, if the migrating group, that is our Rm, if it can take the responsibility for this type of positive charge in the transition state, then it will be more stable. So more stable is the charge in this Rm, that is a migrating group, the faster is the rearrangement, and that is why here the secondary alkyl group is migrating. Methyl group is not migrating, because we know this group is it is more able to stabilize this positive charge, right? So based on this logic, now you can see this is the order of migrating capability. So 3 degree alkene, then we have cyclohexyl, 2 degree alkyl, then benzyl group, aryl group, or it may be simply pH. Now here one thing is interesting, that it is almost same. Sometimes you will see the, rather than saying it is very high, it is almost same, right? So when we are having this type of order, one extra thing I will like to mention here as a side note, that though we have not written here H, but basically H is even greater than 3 degree alkyl. Now why I have not mentioned H? Because if one of the R group is H, it is basically aldehyde, suppose something like this. Now if it is aldehyde and if H is having maximum migrating ability, that means oxygen will be inserted somewhere here. So what you will get? You will ultimately get RCOOH. That means you will get carboxylic acid. But that is not our part of discussion for VVO, that is Baeyer Villiger oxidation. But it is interesting to know that H will be having, that is this order, it will come at the first point. Okay. Now if it is so, okay, see here aryl group. Now if you are thinking that positive charge, if it is stabilized, then how pH group it will migrate, because positive charge we know when we have any aryl group, and positive charge directly on it is not stable, right? But still it can happen. So how aryl group migrate? If this question is arising in your mind, the answer is, see here we have taken, suppose methyl group on one side and another side you have a pH ring. Now this aryl pi bond, it can act as nucleophile. So this lone pair, it is making a double bond here, and instead of the whole pH moving, that is migrating, what is happening here? The double bond is only interacting with this oxide. Now there will be a 3-membered ring generation, because this is the connection point, and this double bond, it is going to, that is, it is going to break, right? And this part is removed as RCOO minus, that is the carboxylate anion. And this is the delocalized carbon, that is the carbocation is delocalized over the entire pH ring, right? So that is why it is stabilized, and in this way it is moving, migrating, it is not that pH is entirely removed and there is positive charge over pH. No, it is not like that. It is going through, it is happening through this pi bond as nucleophile. And finally we are getting, after this 3-membered ring is broken, so this bond is going to break, right? And here this new CC double bond and this oxygen carbon bond, that is the newly generated bond. Now finally there will be deprotonation. This proton can go here and we are getting finally our product. So in this way the aryl group is migrating. Now the summary we can say, as you can see the order for migration. So the electronic factors, the ease of migration is related to the ability of the migrating group to accommodate the partial positive charge. Remember the picture, that is a transition state, what is happening there, that we have just seen. So electron withdrawing group attached to potential migrating group, suppose specifically halogens, they obviously will inhibit migration. So we will prefer electron donating group. So this is the order for migrating aptitude. Now for diaryl unsymmetrical ketone, suppose one side we have simply pH, another side we have any substituted pH, or it may be some OMe group. Okay, so the more electron releasing group will typically migrate. So if it is pH and to substituted pH, obviously pH will migrate. If it is pH and OCH3 substituted pH, then this OCH3 substituted pH will migrate, right? So that is mentioned here. And suppose there is an ortho group, that is ortho effect in diaryl ketone. If the aryl group contains an ortho substituent and another group there is no ortho substituent, migration is hindered relative to an aryl group having no ortho substituent, and that is related to some steric reason. Now remember, very important point, though until now we have discussed about these electronic factors, but you have to remember that steric factor, conformational constants, reaction conditions, everything, all these influences also present. And if you are interested in details of this migrating aptitude, that is not just electronic factors, how the other factors also they operate, then you can consider the book G. Jack Lee, Name Reaction. I will give the details of all the books from where I have used some examples in the description box. Please check there, okay? Now the chemoselectivity part, that is, we will end with this. So which one will predominate, and that depends. Now chemoselective means, if this is our substrate, you can see there is a C double bond O and there is a CC double bond O. Now when you are using PAR acid, there is a chance that the CC double bond, that can also be that it undergo epoxidation. So that is chemoselectivity. Which group will actually take part in reaction? Is it C double bond O or it is C double bond C? Now which will it predominate? That depends on, there are several factors on which it can depend. So for example, in this case, see, if it is MCPBA, we are getting epoxide, and this is this group is intact, right? Now if you are using this type of It is not exactly par acid, it is a mixed form of H2O2. This example in the first slide I have already used. So now we are getting a Vivio product. This is the Vivio product, Baeyer Villiger oxidation. You can see the ring is expanded from 5 member to 6 member, and CC double bond there is no effect. Yield is slightly less, but why this type of that is detailed discussion we cannot do here, because that will take a lot of time. But remember, it depends on, there are several conditions. So sometimes you can see electron poor CC. Suppose the CC double bond is electron poor, and if oxidation is to take place, obviously that will not be favorable condition. So electron poor CC, even if it is present, it can remain still intact. And strained ketone tend to favor Vivio. So electron poor CC will favor Vivio, and strained ketone, because after Vivio reaction the strained that will be released. Okay, that is why it will tend to favor the Vivio. Then controlling some reaction condition by proper choice of peroxy acid, it is often possible to favor Vivio over epoxidation. So the books that I will mention in the description box, you can check the details. Now one more example, as you can see here. Here this CC double bond is intact, only this CO double bond is taking part, and this is actually the Vivio product. We are not seeing any epoxidation. So this example is taken from Clayden, right? So what is happening here? So when, suppose there is no C double bond O, forget about it. If MCPB is present, this side, and also forget about this group for some time. Suppose if you simply have this and double bond, normally this side is preferred rather than this endo side. Exo side is favored, right? But what is happening here? In this exo side, you also have this large group. So both side is becoming now statically hindered. Without this CH2OBN group, that is benzyl ether, there is static hindrance from this lower position. And sorry, what I am saying, without this group, this side is favored, that is the attack from the upper side. But when this type of large group is present, now the lower side is also, there is problem. So attack from both sides is not statically hindered. So what will happen? Now MCPB, it will prefer to attack this C double bond O. So that is why this is completely intact. Maybe if this group is not present, then there will be some epoxidation also. But here we are getting Vivio product. So we have today discussed mechanism, chemoselectivity, regioselectivity. We have seen the details of the transition state, why this migrating group is migrating, some specific groups are migrating. But without diverse example, it is really difficult to understand this reaction in detail. So in the next video, I'll discuss some examples. Okay, so that's all for this video. Thank you for your precious time.